All right, friends, one last lesson. After today, if you're in Canandaigua Academy's AP Calculus BC, after today, it's a couple days of review, some practice with some long answer questions, and then we just go for it. That's our plan. That's our plan. Test next week. But before we can get there, we've got to talk about the alternating series test because we have deliberately avoided series with negative terms until today. And we do so because the test is rather easy to implement. It's a nice way to end the unit. It gives us something that we can do with skill, and it actually is very helpful to us in analyzing series. The alternating series test says, let's pretend you have a series. It's the sum as n goes from 1 to infinity of negative 1 to the n plus 1 times sum a sub n. And what that means is you have a first term minus a second plus a third minus a fourth and so on. That series converges if all three of the following are met. Got to have three things for the alternating series test to apply. One, the a sub n's have to be all positive. And the reason the a sub n's have to be all positive is because the series actually has to alternate. That's a question you ask yourself. Do the terms actually alternate? The only way to get alternation with these plus minus is if the a sub n's themselves are all positive. Second, a sub n has to be greater than or equal to a sub n plus 1 for all n. In other words, you have to ask yourself, do the terms get smaller? It only makes sense if the terms get smaller. And then thirdly, the limit of the a sub n's has to be 0. Do the terms get closer and closer to 0? And all of this only makes sense if you understand what the alternating series test is doing. So here's a number line, which, as we've always said, is a line with numbers on it. Let's look at what the partial sums do. The partial sums. Here's 0 on your number line. The first partial sum is the sum of the first term. That's a1. So we head over here to a1. Now we go back to the left, a2 for the second partial sum. Second partial sum is a1 minus a2. So a2 brings us back here, but not as far as a1 was, because a2 is less than a1. And so here is the second partial sum. And then the third partial sum is the sum of a1 minus a2 plus a3. So a3 is going to take us back this way, but not as far as a2 did. Here's the third partial sum. And so you keep doing this back and forth, but never as far as you were before. And so eventually, what has to happen? Since we're going back and forth, less and less each time, and eventually the back and forthness approaches 0, the series has to settle down. Get a wife, couple of kids, stable job with the possibility of advancement. The series has to settle down. But if any of those things, if any of those three conditions are not met, then the argument we just talked about doesn't work. And if the argument we talked about doesn't work, then we don't know if the series converges. Okay? So you've got three questions to ask yourself when you see an alternating series. One, does it actually alternate? Two, do the terms get smaller? And three, do the terms get closer and closer to zero? If those three questions are answered yes, we say yes, the series converges. Let's consider the following. Let's consider the alternating harmonic series. It's an alternating series. It's called the alternating harmonic series because it looks like the harmonic series, except that it alternates. Do I know that this thing converges? Well, I'll ask myself, do the terms actually alternate? Well, 1 over n is always positive, and we've got the plus minus thing going. Check. Do the terms get smaller and smaller? Well, 1 over n is a decreasing function of n. Yes. Do the terms get closer and closer to 0? Well, as n gets large, what is happening to 1 over n? Yes. This series converges by the alternating series test. We knew that because of the alternating series test. Now, that's a little bit interesting because the actual harmonic series does not converge. The actual harmonic series diverges. We proved that by the integral test. But the alternating harmonic series converges. So let's ask the follow-up. How many terms are necessary to obtain a partial sum within 0.01 of the actual sum? Now, here's the kicker on this. The truncation error on an alternating series is less than the first omitted term. So what does that mean? That means if I write out a whole bunch of terms and cut the series off, I say I'm just going to cut you off after, I don't know, a zillion terms. Then I look at the first term that I left out, and the actual difference between my partial sum and the actual sum has to be less than that first term that I left out. And it has to be because we know that the terms are getting smaller and smaller and bouncing back and forth. So I've got this series. And eventually, I'm going to find a term that is less than 0.01. Less than 0.01. So I think to myself, this is going to be a plus 1 over 99 minus a 1 over 100. Whoa! That's interesting. If I were to cut off right here, if I cut off right there, then the error on that is less than the first term that I left out, which is what I wanted. And so all I have to do is add up these terms, and that partial sum will be within 1 over 100 of the actual retail price. And so 99 terms are necessary. Could we add more terms? Sure we could, but if we add 99 terms, then we know for certain that the error is within 1 over 100, because that's the first term that gets left out. All right. All right. Time to play everybody's favorite game. Does it converge? Does that converge? Does that converge? Does that converge? So hit the pause button, take a look, see if each of these satisfy the alternating series test. Go ahead. Oh, you're just going to do it in your head. You're not going to hit the pause button. You're going to wait for me to do it. Okay, so you did. That's good. That's good. I'm glad. Let's play. Does that get smaller as n gets large? No, the numerator is exponential. The denominator is a polynomial. This does not converge because the terms don't approach 0. Terms don't get smaller as n gets large. Terms get larger as n gets large. But certainly the terms don't approach 0. That's enough to kill the whole thing. 2! Those are positive. Terms get smaller. Terms get closer to 0. We say yes. Yes. 3. Terms get smaller. They're positive. Terms get closer to 0. We say yes. I bring up the following side note. La. These series converge conditionally. What do I mean by they converge conditionally? See, here's the funny thing. Take a look at the green series for a moment. Take a look at that series. If the alternation wasn't there, if we just had the thing circled in green, would that converge? Well, you would say, this doesn't matter, this doesn't matter, this doesn't matter. I got 5 over n. But 5 over n is basically the harmonic series, and the harmonic series blows up. Similarly, with the blue guy, take a look at the blue guy, we would say the 2's don't matter, and we'd get n to the negative 1/2, and that's a p series, and p is less than or equal to 1, and so that would diverge. So when we say that a series converges conditionally, we mean that the alternation is the condition under which the series converges. If it were not for that alternation, the series would not converge. So we say if a series converges only because of the alternation, it converges conditionally. How we doing? Okay. Time to play a nasty game. Find the interval of convergence. Because see, now we can begin to put everybody together. Oh, now we can. It's a little scary. It's an alternating series. Just to write out a few terms, if n equals 1, that's x squared over 2. If n equals 2, that's x to the 4th over 4. If n equals 3, that's x to the 6th over 6, and so on. I want the interval of convergence, all values of x for which that series will converge. So, when I'm asked for an interval of convergence and my series is not geometric, I have to make it geometric somehow. Row, row, row your boat gently down the stream. It's the limit as n approaches infinity of the absolute value. See how important the absolute value becomes now? Because we have an alternating series and we just need to get rid of that negative 1 term of the n plus 1th term. Everybody be really careful with your exponents because n plus 1 replaces n, and so you get like that over the nth term. Time to do a little bit of algebraic simplification and then a little bit of limiting. x to the 2n, x to the 2n plus 2 leaves me with an x squared, negative 1 to the n, negative 1 to the n plus 2, that's, shouldn't have been n. Good call, people at home. That's an n plus 1. Good call. Good call. Then I look at this, and I think as n gets large, that's pretty much 1. So what have I got? I've got the absolute value of x squared. And the ratio test says that this series will converge if that is less than 1. So I know that my interval runs from negative 1 to 1. I know that between x equals negative 1 and x equals 1, my series will converge. I know that beyond x equals 1 and beyond x equals negative 1, the series will diverge. What I don't know is what will happen at x equals negative 1 or at x equals 1. And so what we're going to do now is we're going to test the endpoints. We're going to test the endpoints. At x equals 1. What is this series? This series is 1/2 minus 1/4 plus 1/6 minus and so on. That's an alternating series test whose terms get smaller and closer to 0. This thing converges by the alternating series test. X equals 1 is included in our interval. At x equals negative 1, I get, no surprise, the same series. This converges by the alternating series test. And so negative 1 is included in our interval of convergence. This is a situation where both endpoints converge. So probably for 5 points on a free response question, could happen. You're going to get some awful series like this. You're going to be asked to run the alternating, you're going to be asked to run a ratio test to come up with an interval of convergence, and then checking the endpoints is going to be either a p-series or an alternating series or an integral test or something that you know how to do but haven't been asked to pull out of your toolbox yet. All right, so I've got to leave you with something. I've got to leave you with something to think about. Here's the series. N goes from 1 to infinity. X plus 2 to the n over 3n. This is x plus 2 over 3 plus x plus 2 squared over 6 plus x plus 2 cubed over 9 and so on. I want to find the interval of convergence. And this is one of those on your own things that you're going to come up with. I'll give you a hint. One of the endpoints converges and one doesn't. So there you have it. We'll talk about this when we get together tomorrow and be glad to do it. We'll see you then.